Oh, thanks. Hi everyone, my name is Yang in Zhang University. Today I will share our latest work, Who to Align with Feedback-Oriented Multimodal Alignment in Recommendation Systems. The pipeline of multimodal recommendation systems consists of 4 parts: features, extraction, modality fusion, fusion learning, and optimization. Because different modalities learn by different pre-trained model, they might not be aligned properly. We demonstrate the multimodal feature distribution of a state-of-the-art multimodal model named Freedom and found a significant disalignment. This misalignment can cause the model to learn incorrect relationships and between the features of different modalities, as it can be shown in this figure. We can see in the figure B and C, these two items has a low rank similarity in each modality, but Freedom learned a high similarity. After Freedom learning, about 30% of these similar item pairs become similar. Therefore, multimodal alignment in MRS is not trivial. However, the bidirectional alignment between multimodals in general proposed multimodals is unreliable for multimodal recommendation system named MRS. In the general proposed multimodal models, image and text are treated as parallel cohorts with equal quality. However, for MRS, the quality of the image and text is determined by more factors, and the user preference is the key factor. For example, for this figure, for a t-shirt item, there are 3 people's like is visual model, and only 1 person like the text model. We consider the visual model is the high quality model, and the textual model is the low quality models. If low quality models align to the high quality models, it may affect the predictions of the user preference. Therefore, the one-way alignment may be more suitable than the bidirectional alignment in MRS. But one-way directional alignment are facing 3 main challenges. The first challenge is how to self-adapt each item alignment direction. For example, for the t-shirt we mentioned above, users may like the visual models better than the textual model, but for the smartphone, maybe people like the textual model better than the user model because of the textual models can concisely describe information like smartphones, memory, screen size, and so on. The second challenge is how to coordinate multiple modalities. If there is an inconsistency in the alignment direction, for example, textual models align to the feature model and ID models at the same time, how should we coordinate the multiple modalities? The third challenge is reducing noise in the item and user alignments. Item alignments based on user feedbacks can be inaccurate due to noisy inputs such as missed touches. So to address the above challenges, we propose a framework named FACO. It consists of 3 main key components. The first one is the item level alignment. The second one is the direction turning, and the third one is the cluster level alignment. We first introduce the first one, the item level alignment strategies. To determine the direction for each modalities on each item, we calculate the interactive user feedback scores for these items modalities. For reducing the resource cost, we only consider the interactive users in one batch. If the modalities M with the modalities M has a lower feedback score than the N, So we consider the direction is M aligned to the N. We use a residual structures to explicitly represent what information needs to be supplemented in this process of aligning from the model M to N, and the loss is the constructed loss. We then introduce the direction turning, which is to coordinate multiple modalities. We show this example. This example shows the problems of misalignment when the visual modalities aligns to both textual modalities and ID modal alignments. The directions of alignments might not match perfectly. As we can see, these two angles is not matched perfectly. So, is the final alignment optimal? We think not. We believe that when the visual model is aligned with both text and ID modalities, all embeddings should lie in the same vector space, divided by two basic vectors: user preference spaces and user preference irrelevant vectors. However, aligning with only the text or ID modalities can bring irrelevant user preference elements. For example, aligning with the textual modality may introduce the irrelevant information like this men's sports black sportswear. And aligning with the ID may introduce the unnecessary aligning with features like these symbols. And if we align with both these two directions, can introduce more irrelevant user reference information from both sides. As we can see, these two user irrelevance information can be input. So to instruct this problem, we adjust the directions by maximizing the user preference scores after alignment, ensure it matches the basic vectors related to user preference. And this way, we can avoid the irrelevant elements like the black symbols. This can be removed. And when we can only keep the elements that match user preference, like this is the final alignment score. So for the third challenges, for denoising alignment for items and users, we propose the cluster level alignment strategy. The above alignments can guide by user feedback at the item level, but the user may contain noise. The alignment based on these user feedbacks may contain noise, may sometimes be inaccurate because of the item level, because the item cluster level alignment does not involve the user feedback. It is more robust and stable. We actually align the assignments to cluster centers, not the real cluster center themselves. This is because the cluster centers are typically obtained by offline strategies like k-means, which is time-consuming. And in contrast, assigning items to cluster centers is done online, and it is more efficient. Especially, we use the codebook alignment approach. Each element in the codebook representations cluster centers. For different modalities of the same item, they should belong to the same cluster center. Therefore, the cluster center assignment method for these modalities should be consistent. We learned this object through these swipe predictions. And the ground truth is another model cluster center assignment. And after is optimal transport algorithm named SIGIR. And similar, the interactive user and item pairs should also have the same cluster centers. So we added this construct as well and use this loss. And finally, we use the multitask loss, and we introduced the recommendation object loss, and with the alignment loss we mentioned above. We conduct experiments to answer the following questions. These following 4 questions. To answer the first question, does FATOS enhance existing recommendation method? This is the setup of the experiment. And FATO is a play and plug framework, and it can be added to any backbone. And in this work, we mainly focus on collaborator filters and multimodal recommendation system. We compare with the latest work, BN3. The alignments, the alignment component in this baseline aligns multimodal contents with ID by maximizing the concise similarity between the textual embeddings, visual embeddings, and the item ID embedding. As we can see, for the collaborative filter backbones, FATOS shows the significant improvement of all backbones and the FATO performance. And after we added FATO to the MRS models, it also can have a great improvement. As we can see, FATOs can show a significant improvement on all backbones and on all data sets. And FATO is better than BN3. We can see BN3 poorly, while FATO is significant regarding the average improvement. So the alignment in MRS requires caution. To answer the question 2, we conduct extensive experiments to show each component of these components in FATOs. As introduced above, the item-level alignment directly is motivated by the assumption that bidirectional alignment might degrade the modality embeddings by aligning a high-quality modality towards low-quality modalities. This raises a question: is it better to use bidirectional alignment for high-quality modalities and one-way directional alignment for low qualities, compared with using one-way directional alignments for all models? We conducted these experiments to answer this question. The scores, whose feedback scores above the thresholds was considered the high-quality modalities. As we can see, results in these figures, one-way alignment is always better than bidirectional alignment in MIS. So the final, we demonstrate the FATO has reduced the largest misalignment in MRS. This is to answer the question 4. We implement freedom with and without FATOs on the baby datasets and visualize its modalities embeddings using TSNE, as shown in this figure. And we can see after we use the FATO, the 3 modalities aligns into one namespace. Okay. Oh, okay. So, okay, I will. So, furthermore, we aim to investigate whether FATOs can improve the quality of the multimodal embeddings. Since we use the GPT-4 to generate images based on the embeddings for better demonstrate purpose, we first use ID embeddings with this prompt to generate the product image and descriptions, and then use imagery and text embeddings before and after to generate its pictures and its description. As we can see in these figures, the generate Okay, I will come. So we can see after the image and the descriptions after photo is close to the user preference image in color and style. And this is the conclusion. We argue that for MRS, the multimodal alignment should not be bidirectional. And we propose the plug and place framework photos. And it has 3 normal strategies. And we do extensive experiments on 3 real-world datasets shows that photos significantly improve all models, including collaborative filters models and multimodal models filters. Thank you.
All right, let's thank SIGIR.